Sì, che c'è? Yes. We introduced some concept on thermodynamics of the fluid, and what I want to do today is complete this thermodynamic scenarios talking about the viscous fluid and the characterization of viscous fluid, and then start together for defining the unsteady compressible potential flow. For this scope, I want first introduce to you just a recap on viscous fluid. And yesterday we introduced the gaseous inequality here, and after this introduction we have discussed using also other equation like the energy equation. We use the energy equation here. We use also the mass conservation equation in the development of this. And at the end, this, and we state that here on expressing internal energy in this inequality, we have the possibility to introduce a fluid instead of a solid, and so on. For a fluid, this function E, the specific internal energy, is supposed to be function of two scalar quantity, one for the mechanic and one for the thermal facts. And so this choice is the choice of internal energy as a function of entropy and volume, specific volume, which is the reciprocate of the density. This is not the only possibility in thermodynamics. There are several possibilities for introducing introducing state equation, and there are others possibility as the introduction of the Gibbs function, for example, as state energy, the other kind of function for scalar function for describing the state of the fluid. After this choice, we found that the inequality can be reduced in these three terms, and in these three terms, one is identical, one has to be identical equal to 0. The other two give the possibility to describe what happens in an irreversible transformation when you have viscous effect or thermal propagation or thermal conduction. Okay, both of them are two irreversible phenomena in the sense that they provide to have positive quantity here for the term 2 and the term 3. When you have 0, the transformation is considered to be reversible at all. Okay, we take this opportunity for the part 3. We have that in the irreversible transformation, the head flux as a direction which is opposite, to be more detailed, with an angle greater than 90 degrees with respect to the gradient. And so in the irreversible transformation, in the head flow propagation, the head flow vector go in the direction which is the opposite to the gradient of the temperature. Okay, so the head flow goes, in quote, from hot portion of the fluid toward the cold portion of the fluid, and this is in the conductive point of view, not in terms of convection, natural convection, mass transportation, or in terms of for this kind of characterization. In the second part, and the last one, we have discussed this term here, and we introduce two partial derivative, one partial derivative of the internal energy with respect to the specific volume, the other one with respect to the with respect to the entropy, and we have demonstrated that one of these is equal to the temperature, the derivative with respect to the entropy, and the other one is equal to the pressure apart the sign in the definition of the pressure, okay? And this also allows to decompose the stress tensor in a part of the stress tensor which is responsible of reversible transformation, and another part of the stress tensor which can be summed both each other, the other part responsible of the irreversible transformation. In the case of a reversible transformation, this V is identically equal to 0, so satisfying the Clausius inequality. The reversible part is an hydrostatic portion of the stress tensor, and this is the portion associated with the pressure. Okay? Please, in any time, not only in static, not only in hydrostatic. Okay? This is another strange ideas of students. As further step, we have given a characterization of a fluid as ideal gas. Fluid is named as ideal gas when the state equation is of this type. And this is explicitly given the dependency of E by the entropy and the specific volume. This is the formula. And we have illustrated that this formula implies that the two famous state equations of ideal gas are included in this definition. Okay? And finally, we show this. We show that the energy equation, introducing the fluid characterization in terms of E as a function of S and T, after the assignment of the partial derivative is associated to the temperature, to the pressure, we have found this equation, and this equation is the entropy version, of the conservation of the energy, stating that this entropy may increase or decrease, so this derivative may be positive or negative, by observing that we may pump heat into the particle through this term, the divergence Q, or we are able to increase the entropy by dissipating phenomena like this, by the product V dot T. Okay? Both of these are responsible of entropy. Note that in the case of unviscous flow, for example, you don't have this term, and if the transformation is so-called adiabatic, so the particle is not able to exchange flux of heat with the other particle, you have 0 here because unviscous, 0 here because you have adiabatic, and so you have also isentropic transformation. This can be easily seen here. Okay, this is the last. I want to close this framework of viscosity and second thermodynamics issues, inequality crisis consequence. I want to conclude this talking about isotropic viscosity. And in particular, one can distinguish a fluid by another fluid, defining how V, viscous stress tensor, which is the irreversible part of T, how V is dependent on the kinetic quantity, in particular is dependent on D. Okay? And this is the constitutive relationship for fluid. Note that this constitutive relationship are establishing actually how the fluid is viscous. Okay? So this is a special kind of constitutive relationship on viscosity. And what we mean for isotropic viscosity? What we mean for having an isotropic relationship between V and D? What is an isotropic relationship between D and V? Okay, this is very easy. This concept can be understood by talking about the isotrope, the spheric and deviatoric part of a tensor. What is the spheric part? If you have a tensor A, the deviatoric part of the tensor A is the isotropic spheric. The spheric part is a spheric, so defined, taking the identity tensor and multiply the identity tensor by the trace of A, which is a number, divided by 3. So take the spheric part is as a component matrix composed by the average of the sum of a diagonal term. AKK means A11 plus A22 plus A33 divided by 3 in the diagonal. This is the trace. This is the spheric part, of A, and 0 everywhere. So when you have a spheric part of the tensor, you are focusing on, you know that generally a tensor is able to take a vector u and transform this vector to another vector v. Okay, so take u and transform u to v. Okay, when you apply, this is a v is equal here to a on u. If you have u and you apply, you apply a spheric on u, you obtain something like this, a longer or shorter vector, but parallel, of course. But the entity of this magnification or demagnification of the vector is given by the trace, is something internal of A, the trace. Remember that the trace over operator is an invariant. This means that when you sum the diagonal term of linear operator, and if you exchange the frame of reference and represent the same operator to another frame of reference, and you again sum the element of the diagonal, the trace is the same. There are some invariants in an operator. The invariant are the eigenvalues and the trace and the determinant. Note that the trace is a sum. Since the trace is an invariant, if you represent your operator in diagonal form, then the trace is also the sum of the eigenvalues. Okay? And therefore, it's an invariant. Okay? And what about the determinant? If you have your operator in diagonal form, the determinant is the product of the eigenvalues. And therefore, the determinant is another invariant. Okay? And this is the story of the invariant. And the isotropic part of a tensor is something related to an invariant part of the tensor. Okay? I take the trace and I distribute, I am spreading the trace on the diagonal of an identity operator. Okay? So this is the spheric part. And therefore, we have a spheric part for our viscous tensor, dV, and we have S. And we have a spheric part for our strain rate tensor, D. Okay? But we can define the rest of the operator as difference between the original operator and the spheric part as deviatoric part. Okay? For example, look here. We have the operator A. If you apply to the operator AU, you have as output V. And this is as output A spheric applied to U. Okay? So, what about the deviatoric part? The deviatoric part is the tensor such that if you apply this tensor to U, you should obtain something like this. In fact, A spheric on U plus A deviatoric on U is give you your original output. And therefore, and that's the reason of the word deviatoric. Look to this vector here with respect to the original word. It's just a deviation for giving you your final value of the vector. And therefore, at the end of the story, we have this deviatoric part, and we also have a deviatoric part. We have also a deviatoric part for the strain rate tensor D, like difference between our original tensor minus the spheric part of D. Okay? In other words, we have defined a decomposition of V in its spheric part plus its deviatoric part. Its spheric part of D the spheric part of D plus the deviatoric part of D. Okay. Go back to isotropic definition. What is the isotropy? A fluid is isotropy if the transformation giving V by D is linear and is such that the deviatoric part of V is proportional to the deviatoric part of D, and the spheric part of V is proportional to the spheric part of D. So isotropy isotropy in terms of dissipation viscosity, okay, implies that the spheric part of D is proportional to the spheric part of D, and the deviatoric part of D is proportional to the deviatoric part of D. Okay, so in other words, you want a stress viscous tensor as dependent on the strain rate velocity of the velocity, strain rate tensor, and you want that the principal direction of D are coincident with the principal direction of V. In other words, the fluid in this case is not able to impose deviation in the stress tensor, in the stress viscous tensor with respect to the kinematic fundamental direction of the flow given by D. Okay? D as a tensor is giving to you principal direction, and you want that this principal direction are preserved in the viscous flow. Okay? And this means isotropy. Now, use this concept for finding this, and in particular express the fact that V is equal to V spheric plus V deviatoric, and this is equal to C1 by D spheric plus C2 D deviatoric by definition. Okay? And this D is given by the difference D minus D spheric, and therefore here you have C1 minus C2 by D spheric plus C2 by D deviatoric. Excuse me, by D total D. I'm sorry. Total D. Okay? And this part this spheric part is given by, if you indicate with theta, the trace of D, D11 plus D22 plus D33, trace of D, you have the following C1 minus C2, and the spheric part is the trace divided by 3 and multiplied by the identity matrix by definition, and this is plus C2D. Or now in fluid dynamics, this quantity are also known as Lamé constant, and we have lambda defined by definition as C1 minus C2 by 3, and mi, the other constant, is equal to C2 by 2. Okay? And so we have inversely that C1 inversely, we have that C1 is equal to 3 lambda più plus 2 mi, and C2 is equal to 2 mi. This relationship, this final relationship, is known as also as isotropic relationship, constitutive relationship, and the fluid respecting this isotropic fluid, in sense of viscosity, this viscous isotropy, this isotropic fluid are also named Stokes fluid.